Hi, we're going to be doing a quick review of Chapter 20, Principles of Chemical Reactivity. And to do this, we're going to use the example of the reaction of hydrogen and oxygen reacting into water. Okay. What a reaction is elements that are bonded together, and this could be covalently bonded, ionically bonded, metallically bonded, and those bonds breaking and new bonds forming and getting either energy out or losing energy in the process. We're going to use the example of water, and this is a covalently bonded material. So what oxygen gas, which is one of the reactants in the chemical reaction, that's a reactant is like the fuel, or what we start with in a chemical reaction. What oxygen molecules look like is this: an oxygen element double bonded covalently to another oxygen element. If we want to look at this in a mathematical way, it looks like this: O2 with a little subscript or a small 2 behind it. Hydrogen is also a reactant, and it is also covalently bonded to other hydrogens, or another hydrogen, and it looks like this with a single covalent bond. And the mathematical symbol for this is H2, kind of just like the oxygen was. And the chemical reaction is the breaking of these bonds by using energy, and so we have isolated oxygens and hydrogens, and those hydrogens and oxygens will want to go to a lower state of energy naturally because they're naturally lazy. And so they'll create bonds between each other and make water. And water looks like this, a picture of oxygen with a covalent bond to 2 different hydrogens, or if we want to look at it mathematically, H2O. Okay. So because we have these mathematical symbols, let's look at an equation so we can know how to balance equations. This is an important skill that you need to be able to perform that we learn in Chapter 20. So this is what a sort of incomplete version of the equation of hydrogen and water, or hydrogen and oxygen turning into water, looks like. I've put blanks here because we're going to fill these in with numbers to show how many molecules we'll have after. So this is hydrogen plus oxygen equals water. The most important symbol here is this equation, this equals sign. Now, I know it looks a lot like this double bond, but it's different. This is just the mathematical symbol, which means that whatever we have on this side of the equation is exactly the same as what we have on this side. Now, there's a problem with the equation the way it looks right now. This subscript, what it means, this little 2, means that in this molecule of water, we have 2 hydrogens. There is no subscript behind oxygen, which means there's only 1 oxygen. And if we look over here, we have the hydrogen and oxygen molecules respectively. This hydrogen has 2 hydrogen atoms in it, in the molecule, and this oxygen has 2 oxygen atoms. So if we were to draw this out, it would look like this: hydrogen molecule plus oxygen molecule equals water molecule. Now if I were to count the amount of hydrogens on this side, 2, and I have 2 hydrogen atoms on this side as well, so we're fine with hydrogens. But we only have 1 oxygen on this side. So there's a way I can solve that problem, even though there's 2 oxygens on this side. If I put a 2 in front of the water molecule, now I have 2 water molecules. So we'll just drop 2 water molecules. And now this problem of not having enough oxygens on this side is solved. But I've created another problem in the process, which is this. Now we have 4 hydrogens on the right side of the equation, and we only have 2 hydrogens on this side. So if I put a 2 in front of this hydrogen molecule, now I have 2 hydrogen molecules. Okay. So now if we look at the equation, it's balanced, meaning that we have the same amount of hydrogens on one side as we do on the other, and the same amount of oxygens on one side as we do on the other. Now we have a blank in front of this, but this is just to show we didn't have to do anything to change the amount of oxygens on the left side to balance the right. And so we could put a 1, but usually in math, if there's a 1, we just leave it blank, and so we'll just erase it. And so this is what the balanced equation of hydrogen and oxygen becoming water looks like. So let's look at this, how it would look like on a graph. Now, just like with the rest of this, this class, whenever you look at a graph, you really need to know what is being graphed. So first, most important, what are the x and y axes? On the x-axis, we have time. And this just means that from this point of the graph all the way to this point, this is the beginning of the reaction and goes to the end, just in time. And on the y-axis, we have energy, or the energy of the electrons in the bonds. Now remember how I said before, in order for a reaction to happen, we need to put energy into it to break the bonds, so that new bonds can be made. And in an energetically favorable reaction, when the new bonds are made, the new bonds have lower energy, so we get energy out of it. So this is what it looks like. The hydrogen, right here, and the oxygen, when we give them energy, this is called the activation energy, the energy required to break those bonds. Once we get to the top of this, and if we want to measure that distance right there, that is the activation energy, or energy to start, or the ignition for the reaction. Once the bonds are broken, these elements, the hydrogens and the oxygens, will start looking around for bonds to make at lower energies because they're naturally lazy. If they find, like in this case, you'll have hydrogens and oxygens together, they're going to find each other. Hydrogens and oxygens are going to make bonds with each other to form water because that's the lowest energy that they can come to. So the energy of those bonds will drop, and we'll see this downward slope on the graph. And they'll even out at the energy of the bonds in water. So hopefully, if you've been following along, you can see how the energy change of the electrons in the bonds goes from up here at the reactants, activation energy to break the bonds, loss in energy as lower energy bonds are made, and we end up at the products. So, this is what's called an exothermic reaction, because what we'd see if we had hydrogen gas and oxygen gas, we ignited them, they would explode. Okay? In order to conserve the energy lost in making lower energy bonds, we can't just destroy it. Where does that energy go? And that's what an explosion is, the heat, light, and sound. And that means that the energy, or the thermal heat energy, is exiting, or in other words, exothermic reaction. Now there are other types of reactions where, making the reaction, they actually make bonds that are higher energy. And this all happens because of entropy, like you learned in chapter 18. They'll end up above where they started. Or in other words, the bonds have higher energy. Where did that energy come from? Well, they took that energy in from the surrounding environment, and this is what's called an endothermic reaction. Or if you were able to hold this reaction as it happens in your hand, it would actually take energy from your hand and it would feel cold. Okay, and that's an endothermic reaction. All reactions will happen spontaneously or sustain themselves if they increase in entropy, because everything is moving toward increasing entropy. So, take-home message from this is, through a chemical reaction, if we end up below the line, the reactants have lost energy in going to the products, and we get that energy out of it in the explosion. Okay, so that's an energetically favorable reaction. And if it ends up above the line, we lose energy. It kind of charges that with more energy in the bonds. The concept that you need to know that's important for this chapter is there are certain materials that can be added to a chemical reaction that will decrease the activation energy, or speed up the reaction is sometimes what's said. And all that does is, for example, in this reaction of hydrogen and oxygen to water, if you have the element palladium, the palladium's not used in the reaction, but it just helps, by its nature, lower the activation energy, and that makes the reaction a little easier to perform. And that is a little review of chapter 20.